Good morning, everybody.
Good morning, Professor Madhav, Professor Sai. Good morning.
Good morning, Dr. Muthukumaran.
Good morning, all of you, sir. Good morning, all of you.
Very
Good morning, Dr. Veena.
Professor Muthukumaran, it is now 9 a.m. Can we
Yeah,
start?
we'll start. I'll formally.
Good morning, sir. Good morning.
Yeah. Thank you for joining with us. Very good morning and warm welcome to all for the third and final day of IGC 2021. So today we have two very exciting event, plenary session 5 and 6. And we do have two more technical parallel session, one in the morning, the other one is in the afternoon. So, and we'll be having a most awaited valedictory function with award ceremony. Once again, I welcome all the members, our IGS members and keynote dignitaries, delegates, all our guests to the last day program. So with this welcome note, I hand over the session to Professor Solanki to conduct the plenary session. Over to you, Professor Solanki. Thank you.
Welcome to chairman, co-chairman, and presenter of this session. I am thankful to the organizer of the event IGC 2021 Trichy for giving me the opportunity to meet you here in this session as a session coordinator. We have Professor Eva Nathan is the chairman of the session, and Professor K.S. Veena is the co-chairman of this session. I introduced the Professor Eva Nathan first. Professor Eva Nathan was a professor in geotechnical engineering at the Department of Civil Engineering at IIT Madras until his retirement in June 2021. He is an active academician, researcher, and consultant in geotechnical engineering. His expertise includes the soil dynamics and earthquake geotechnical engineering and ground improvement. He has guided 16 PhD, 11 MS by research, and several MTech students. He has authored over 196 scientific publications, including over 62 articles in referred journals. He is an editorial board member for the Journal of Earthquake and Tsunami. He was the chairman of the Indian Geotechnical Society IGS Chennai chapter during 2012 to 17, IGS National EC member during 2014 to 17, and is currently a National Executive member of the Deep Foundation Institute of India. He is member of several technical committees of the International Society of Soil Mechanics and Geotechnical Engineering. He has received the IGS 3 MSJ Biennial Prize in 2004 and the IGS Professor C.S. Desai Biennial Prize in 2012. He is honorary fellow of the National Engineering Academy of the Republic of the Kazakhstan. We welcome you, Professor Eva Nathan, for your presence as a chairman here in this session.
Thank you.
We have with us Dr. K.S. Veena. She is the co-chairman of the session. Dr. K.S. Veena is presently working as a professor at Cochin University of Science and Technology. Her area of interest includes the geotechnical engineering. She coordinated the TechWeb 3 sponsored expert lecture on finite element modeling delivered by Dr. Sunil Kumar and Professor of Division of Civil Engineering, CUCK 2020. 5 days online expert lecture series on smart geotechnical engineering, symposium on landslide analysis, mitigation, and case studies in association with IGS Kochi chapter and McAfee. She guided PhD, MTech, and BTech students She is a lifetime member of the Indian Geotechnical Society, Indian Technical Education, Indian Road Congress, etc. She has several publications in international national journals, conference seminar proceedings, and book chapters. In this session, I welcome Professor Eva Nathan and Dr. K.S. Bina for their presence, and I hand over the session to Professor Eva Nathan and Dr. K.S. Bina. Thank you.
Thank you, sir. Thank you, sir.
Thank you. Thank you, Professor Solanki, for kind introduction. Good morning to everyone. I first thank the organizers for requesting us to chair and co-chair this session. I welcome all of you for Plenary Session 5, which includes 3 keynote lectures from eminent persons from the field of geotechnical engineering. First lecture by Professor Sanjay Kumar Shukla from Edith, Cowan University, Australia. Second keynote lecture by Dr. R. Chitra, Director, CSMRS, New Delhi. Then third keynote lecture by Professor Buddhima Indraratna, University of Technology, Sydney, Australia. Of course, the first lecture will be Professor Sanjay Kumar Shukla, who is a well-known person, not only in India, throughout the world. Anyway, for formally, I will briefly introduce him. So, Professor Sanjay Kumar Shukla is a founding research group leader, Geotechnical and Geoenvironmental Engineering, School of Engineering, Edith, Cowan University, Australia. He is a founding editor-in-chief of International Journal of Geosynthetics and Ground Engineering, which is very popular among geotechnical engineers. He holds a distinguished professorship at 7 universities, including Delhi Technological University, Delhi. He has authored more than 270 research articles, including about 170 referred journal publication. He's co-author and co-author of editor of 23 books, including 7 textbooks and 22 book chapters actually. And in 2020 and 21, his 2 IC textbook has been ranked #1 by Amazon. He has been honored with several awards, including the most prestigious IGS Award 2018 from International Geotechnical Society, USA. He serves on the editorial boards of 9 international journals. He is a Fellow of Engineers of Australia, Life Fellow of Institution of Engineers, India, and Indian Geotechnical Society, and a member of ASC and several other professional bodies. So with this introduction, I welcome Professor Sanjay Kumar Shukla to give a topic on wraparound reinforced technique for strengthening the soil foundation, a sustainable approach. Thank you. Professor Shukla, please.
Please unmute Professor Shukla. Professor Shukla, you are not, your mic is mute. Please unmute. Okay. Yeah, please.
Thank you, Professor Eva Nathan, for giving me this opportunity to deliver my talk in this great conference, IGC 2021, which is being organized under the leadership of Professor Muthu Kumaran. I can see since it's a start that it is being organized in a well-planned manner. And today, this is a time for me to share some of my experiences on this topic. So let me share my slides first. Can you see now? Is it visible? My screen?
Visible, but
you need to make a full screen. Okay.
Okay.
Yeah, full screen. Yeah, full screen is there. Let me move this. Sorry. Just a minute. Let me move this. Okay. So the topic is wraparound reinforcement technique for shallow foundations, a sustainable approach. These days, we all know what is sustainable development. Basically, sustainable development is a challenge of meeting human needs for natural resources, industrial products, energy, food, transportation, shelter, and effective waste management while conserving and protecting the environmental quality and the natural resource base essential for future development. Not only in geotechnical engineering, in all areas of our life, the researchers, engineers, common people, they are trying their best how we can make the development sustainable. Here, I am going to talk in our area, geotechnical engineering, especially in shallow foundation, how we can try our best so that the reinforcement of the soil mass, foundation soil, can be meeting some aspects of sustainability. So we all are very much familiar that the basic concept of reinforcing the foundation is laying geosynthetic layers horizontally, 1 layer or 2 layers, 3 layers, 4 layers. Researchers have done a lot of experimental studies, especially a small scale laboratory test, and very limited large scale tests have been conducted. But as happens in our civil engineering, not easy to have large scale tests, and we are really, our design is based on certain constraints, because our knowledge comes from a small scale testing in many cases. So in most cases, what has happened that researchers have said, okay, we can go maximum, let us say 3 to 4 layers, and for reinforcing the foundation. And many papers we can see in research literature. So this is a loaded footing resting on the reinforced foundation. This gives us a very basic concept about reinforcing the foundation soil. Now, another line sketch is how we can, improve the load carrying capacity of the breeze abatement foundation soil by inserting geogrid layers. Reinforced foundation soil provides improved load bearing capacity and reduced settlements by distributing the imposed loads over a wider area of weak soil. This is very much known to all of us. What are the benefits? We are improving the load bearing capacity. We are trying to reduce the settlements, and all happens because of distribution of the loads over wider area over the weak subsoil. Also, the improved performance of a geosynthetic reinforced foundation soil can be attributed to an increase in shear strength of the foundation soil from the inclusion of the geosynthetic layer. We have experimental studies reported in literature that if we are conducting triaxial compression test with reinforcement layers 1, 2, 3, 4, and researchers have said that yes, there is an increase in shear strength of the reinforced foundation soil. Now, question is, what can be the ideal reinforcement pattern? And this is very much reported first by Bassett and Last, and I also reported in my books that this is the ideal reinforcement pattern. So in ideal reinforcement pattern, the reinforcement is almost horizontal in the central part, you can see here, but when we are moving away from the footing base, it is curved. So basically the orientation should be in the direction of principal tensile strength. But there is a practical difficulty. And that's why we go for practical reinforcement pattern, which is horizontal layer. So because it is not possible to install in the direction of principal tensile strain. So engineers are installing in horizontal layers. In the end of my talk, I will share with you one case study where geogrid layers have been effectively used in the field project, the way we are able to see in this line sketch. Now, reinforcing mechanisms and functions are very much clear to all of us. I'm not going to give more time on this, but I am just summarizing that shear stress reduction effect. We know what happens that when we have geosynthetic reinforcement, the mode of failure is going to change from local shear to general shear failure. Now, another benefit is slab confinement effect. So with presence of geosynthetic reinforcement, we can see what is happening, that the stress distribution that is going to be different. And we can see that this is happening because of confinement effect, or we say slab effect. Membrane effect helps us in supporting the vertical load directly because of one component of the tension is going to be in the vertical direction. And many of us in India, we have done analytical studies to explain and some mathematical developments. Now, anchoring effect is very much known, and we know that what happens if particularly when we are using geogrids, particles can pass through the apertures, and there is passive resistance under the applied load because against the geogrid ribs there is passive resistance, and that helps us, in improving the soil capacity. Now, separation effect, even though there is no tension in the geosynthetic reinforcement layer, because by reinforcement we generally say that there will be some tensile force, but even though there is no tensile force mobilization, because of separation we get benefits. So we can summarize here, under the reinforcement function we have shear stress reduction effect, slab confinement effect, membrane effect, anchoring effect, and in separation effect we don't have tensile stresses mobilization, but still we have benefits. And there is a question that under what condition we can say that separation is primary or reinforcement is primary. In this diagram we can see on x-axis sigma over Cu. So sigma is the stress over the foundation soil and Cu is the undrained cohesion. So what happens that if sigma by Cu is approximately, you can see here, 8. So if sigma by Cu is lower than 8, we can see in this diagram that benefits come mostly from separation. But if sigma by Cu is greater than 8, maximum benefits come from reinforcement. And this has been reported in the even third edition of my book, Handbook of Geosynthetic Engineering. And initially it was shared by Nishida and Nishigata in 1994. So this is very important research finding, and I have carried it in my books because it explains very clearly under what condition we can design our foundation for separation function or reinforcement function. That's why it has practical value. Now, coming to geometrical design parameters, whenever we are going to design a reinforced foundation, we need to decide what is the value of U. the depth of first layer of reinforcement below the base of the footing, a spacing h, the maximum depth of reinforcement, how many layers, and now I am coming to B, width of reinforcement. In this conventional reinforcement technique, what is the value of B? Researchers have reported, based on the experimental findings, numerical studies, that this B can be even 2B to 6B. There is wide variation, right, in the research findings that we need at least 2 times width of the footing, that much. And at many places, we are not going to have that much land available, especially in urban areas. So how we can try to minimize the land width, that is the question. And moreover, if we are going to use, let us say, 1 layer, 2 layers, or 3 layers, still with the same amount of reinforcement, we can further increase the load carrying capacity. We can further reduce the settlement. So that will bring some aspects of sustainability. That is the main theme of this wraparound reinforcement technique. Now, before that, I would like to just here present how we evaluate the benefits of the reinforcement. Bearing capacity ratio is a very popular technical term we are using, BCR, which is the ratio of the value of the load bearing pressure, which is in the case of reinforced condition, and what is the ultimate bearing capacity for unreinforced soil. So bearing capacity for, we can say, for reinforced condition and for unreinforced condition here, right? And we can see that in case of reinforced soil, we have benefits because we are getting for the same settlement. So we need to compare this bearing capacity ratio, which is basically defined for the same settlement. So for the same settlement, we can see that BCR is going to be higher. There can be other ways, but this is the most common way as we know how to assess the benefits of reinforcing the foundation soil. Now coming to wraparound reinforcement technique, which I developed during 2007 and 2008, and I applied it in real field project at a time when I have only concept in my mind. I had no rational basis, but I did some calculation, and later what happened, those concepts have been verified by experimental study, numerical study, analytical study. So I am going to share some of them. So here, this diagram indicates how we are going to reduce the land width. So B prime is going to be lower than B. So this is one of the key advantages of wrapping the edges of the reinforcing layer. And we are going to have additional benefits, which will certainly bring sustainability in our construction practice. So in this case, you can see here another comparison that with no wraparound ends, the width is much higher compared to the case when we are going to recommend wrapping the edges or ends. So here we have lap length L. That is the design variable, we can say. So this is advantage. So let me summarize here. Benefits of wraparound reinforcement technique: additional improvement to the load bearing capacity, additional improvement to the stiffness in terms of modulus of subgrade reaction. We have experimental and numerical findings on these aspects. Reduction in width of land required for construction of foundations. reduction in cost of the project significantly, especially in urban areas. So these are the benefits which really help us achieving the sustainability in our foundation design and construction. Now, I am going to share some of the experimental studies which have been carried by my research team. Although, as I said, that the concept has been developed and I used it and reported before before many experimental research studies successfully, but this is the first experimental work on this technique. And in this technique, this is a simple test, testing in a test tank, and we can see the footing, we can see hydraulic jack, and we have applied the load and we have compared for 2 cases. And as you can see in this diagram, what is happening. So on x-axis load bearing pressure, on y-axis settlement ratio, S by V, and we can see unreinforced soil case and reinforced soil without wraparound ends, reinforced soil with wraparound ends, and the details can be observed in Indian Geotechnical Journal. We published, our first work has been published, and we are fortunate that Indian Geotechnical Society awarded this research in 2016. Now we can see here another graphical presentation that indicates that we are getting benefits with wraparound ends. Okay, so wraparound ends are giving benefits in terms of ultimate load bearing capacity of reinforced foundation soil for different embedment depth ratio D by B. Now, we all know that how many model tests have been conducted worldwide? A large number. But how many tests have been conducted in water environment? Very, very limited. Probably this may be not the first, but I can say that very initial first works that considered submerged conditions. It is difficult because once we have to we complete the test, disposal is also a problem, especially in our laboratory environment here, not easy to go for disposal, but we have successfully conducted, you can see, in submerged condition. And interesting data you can see, there is no applied load, but still there is a settlement, even for relative density, because we have here in Perth sandy soil. So Perth sandy soil, even though we try to achieve 90% relative density in compaction, and when we have all set up, what we observe with the rise of water table, there is a settlement. So this is without loading also, but we can see the advantages, right? No reinforcement and reinforcement with wraparound ends. So we have seen that wraparound ends are helping us in improvement of load bearing capacity for a given settlement. Here another presentation, which is on y-axis, you can see ultimate bearing capacity and with number of reinforcement layers. So more layers will certainly benefit, but really no need to go beyond 3, because we can see they are all parallel. That means there is no really significant improvement after 3 number of layers, even in with wraparound edges. Now we have here plotted modulus of subgrade reaction. I said that stiffness also increases, and we can see here that with wraparound ends and for different dF by B ratio, means embedment depth. So advantages can be seen, and this is for 70% relative density and with a different number of layers. Now, another plot here for embedded footing, because we initially conducted for surface footing, later for embedded footing. So in case of embedded footing for 3 different relative densities, but for a given U by V 0.3. And we can see that wraparound ends are helping us improving load capacity, and we can say that there is reduction in settlement as well. If you talk, in a relative manner, that if you are talking for the same settlement, then we have to say that improvement in load carrying capacity for a given applied pressure, we can say that we can have reduced settlement. Now, in addition to experimental studies, we have also conducted numerical investigation using commercial software Plaxis, and you can see some of the diagrams here. Refined mesh zone, and here later what we did that we have even some more study with full wraparound cases, right? So what happens in full wraparound case, we have compared, we can see here I think better, and we have also measured pressure distribution, right? Pressure distribution, strains within the reinforcement in both cases, no wraparound, with wraparound, and we published a good paper in ground improvement and later in geotechnical later as well. So let us see here, I think very interesting finding we can see here. On reinforced case, this is the diagram, double layer, this one, and fully wrapped here. So this is a fully wrapped. It means this diagram clearly shows that if we are going to recommend 2 layers, it is better to recommend 1 layer with full wraparound edges. So because for a given settlement, we are going to achieve higher applied pressure. So recommendation can be in place of 2 layers of reinforcement, 1 layer but with wraparound edges. In principle, it looks that there is no big difference, but yes, there is a difference. And recently, that we have published the mechanism of wraparound ends, and we have now analytical formula like Terzaghi bearing capacity equation. I have not included that here, but in geotextile geomembrane, we have a paper for calculation of load bearing capacity, and with explanation of mechanism that when we have wraparound edges, there is confinement. The way we see these days, even in Geoshale, right? But Geoshale is a different case, and we cannot recommend everywhere Geoshale. Just see at this project. This is a geograde reinforcement at the excavation base. And
Professor Shukla, could you please?
Yes, just within 1 minute. So this is a case study you can see published in International Journal of Geosynthetics and Ground Engineering in 2015. Geogrid reinforced granular pad foundation resting on loose and soft soil, Hamilton Harbor, Ontario. So you can see how geosynthetic layers have been installed, but not with wraparound ends. If they could have been used wraparound end, certainly additional benefit as I discussed. And this is the finished construction, completed tanks on that project site. So we have many applications, but unfortunately formal reporting is limited in our research literature. And I do believe that in future we will have more case studies. And just I am sharing that first time I reported that wraparound technique in my IC textbook, Core Concepts of Geotechnical Engineering, later in Introduction to Geosynthetic Engineering, and more recently in 2022 edition, wraparound technique has been given in this IC Handbook of Geosynthetic Engineering. Thank you for hearing me with great patience. and any questions, if there is from audience participants, I will try to answer suitably.
Thank you, Professor Shukla, for your excellent presentation. I have one question. This wraparound technology, how it will perform under earthquake loading conditions?
Under
Earthquake loading conditions.
earthquake, yeah. You see, I do believe, because only one study has been conducted by my PhD student on repeated loading. Really, not that is not cyclic loading. So more research is required. But I do believe that because of wraparound edges, if there is vibration, let us say, right? So what will happen that in vibration we have experienced that there is lateral spread, vertical deformation. So wraparound edges will confine under vibration, and certainly that will help better compared to no wraparound edges. But currently there is no scientific study, only for some repeated load we have completed, and advantages we can see in that repeated load.
Thank you. Professor Bina, do you have any observations or questions? Okay. Okay. Any other questions from the audience? Kindly mute and you can ask questions if you have any questions.
Bhuminathan sir,
Yeah.
there may be option for those who are seeing the live stream. They may write in the chat also.
Yeah, the chat will come here, I think, most probably. I don't know.
Okay.
Here in the chat, no question. So Sabina, do you have any questions or observations?
I also found that this wraparound technique is very useful. We have done some small embankments with the wire geotextiles, and we found that it is very useful and convenient, and also for the construction. Actually, what I feel is we need more analytical methods for this wraparound technology. We have to think about that in that direction.
Thank you.
Yeah, I mentioned that for one case, for a steep footing, we have developed analytical expression that is in geotextile geomembrane paper, and that can be even used for a square footing. So with a different shape factor as we do in Terzaghi generalized bearing capacity equation. So, but certainly, as you said, that for dynamic condition, we need to focus on that how we have rational methodology.
What I feel is analytical methods, analytical publications dealing with analytical methods in this wraparound technology is very less. So
I agree. I agree. That is the first work which is in geotextile geomembrane. We have published recently, and in future, I think more. Suppose that bearing capacity factors for reinforced foundation soil, so that equation can be utilized, in a more scientific way in future.
Bhuminathan sir, some questions are written in the chat.
There are a few questions.
Yeah, I can see question. I can see question myself.
Yeah, you can answer, or I can read the question.
Let me answer. One question is from Dr. Shiva Raman. How can we distinguish geoshale and wraparound geogrid? Very good question. That in geoshale, that we have a small size cells, and that confines the soil all around, and that is a very good concept. So in wraparound geogrid, if we see the soil mass in the wraparound edges, similar condition is there, the way we see in a confined cell, because there is, passive resistance, and that helps in improving the, basically you can say, the strength of the soil because of that. So the difference, I will say, in application, from application point of view, that if you are going to have, let us say, a thick depth of layer for foundation preparation for heavier structures, I think Geoshale, still someone can say, why not Geoshale in 1 layer, 2 layer, 3 layer, or large Geoshale? We have site assembled Geoshale as well, even 1 meter depth. So we have to see the cost also, that in Geoshale we are using more materials, polymeric materials, compared to the way I am talking about wraparound reinforcement layer. So it is all relative, situation, field situation, we have to compare. But there is some similarity as far as the mechanics is concerned, in derivation of mathematical expression or analysis. There is one question by V.S. Somia. What is the construction sequence for this technique in real field problem? I think very interesting question. You see, as I did during 2007-2008, the edges I had not covered, right? So I asked that, okay, let us place the soil in the central part. So we should keep some length of the reinforcement free, so that we can have that, wrapping and filling the side soil, and then the top layer can be placed and compacted as we do in normal compaction. So this I can answer to that. Then third question is from Parth Trivedi ji. Why beyond 3 layer no significant improvement? Very good question. Because you see, we are applying the load through the base of the footing. So there is load spread. And if we are going to have, we can explain this on the basis of a stress distribution, because the stress is going to, decrease with the depth. So the reinforcement is not going to be effective, because that is not going to be stretched along, right, more. So stretching is required for reinforcement function. So if 4th layer, 5th layer, there is no real, stretching, means a kind of interaction of the soil and geosynthetic opposing each other when more than 3 layers. And this has been even in 1975, first study, not with geosynthetic, Binkett and Lee, they have also said that more than 4 layers is not required. So reason, as I said, that space is going to decrease, and there is really no mobilization to cause stretching over the geosynthetic reinforcement.
Thank you, Professor Shukla, for giving nice explanation for all questions. And also on behalf of the organizing committee IGC 2021, I thank you for spending your valuable time to share your ideas with us actually. Thank you once again. Thank you.
Thank you, sir, for giving me this opportunity to deliver my keynote talk. And I congratulate you all for this successful IGC 21, which is continuing. I don't know how many years, you know better. We have been regularly organizing every year with so much involvement and enthusiasm. So congratulations to the team of IGC 2021.
And next time it is in Cochin, sir. You are welcome for that also.
Yes, yes. We are always together. We are always together. As I, every day, many of us know. Thank you.
Yeah, thank you. Professor Veena, please take over.
Yeah. I'm very happy to introduce the next speaker, Dr. R. Chitra. She is working as director at Central Soil and Materials Research Station, Department of Water Resources, River Development and Ganga Regeneration, New Delhi, Ministry of Jal Shakti. She has 33 years of experience in the field of geotechnical engineering. Her experience in planning, guiding, and execution of geotechnical investigation works for river valley projects has spread to over 350 projects within India and neighboring countries such as Nepal, Bhutan, Afghanistan, and Myanmar. Her interests include hydropower development, earth and rockfill dams, problematic soils, risk assessment of dams, numerical modeling, ash containment systems, fly ash characterization, geosynthetics in water resources, artificial neural networks, and quality control of hydroelectric projects. She has published more than 250 technical papers in various international and national journals and conference proceedings. She is member of the expert committees of most of the dam safety review panel, major dam projects and irrigation projects. She is also a member of various committees of national repute like BIS, IRC, etc. And she has contributed for formulation, review, and updation of various Indian standards codes. So with great pleasure, I invite you, Madam, for this on behalf of the organizing committee of IGC. We welcome you, Madam, for the presentation. Please.
Thank you so much. Thank you so much for the introduction. I think my slides are seen by everyone.
Yeah.
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 Okay.
Okay.
So I'm here to talk about geological surprises and the challenges in geotechnical investigations project. Since I am working in the Ministry of Water Resources, the Ministry of Jal Shakti, Department of Water Resources, Ganga Regeneration and River Development, I will be remitting myself to the projects under hydroelectric projects. So Central Soil and Materials Station is the research organization working for the water resources sectors only. But we are not limited to the only water resources sector. We are looking after the road sector if required, and railways, as well as the thermal power sectors as well. So while if I talk about the construction of dams in the world, the ICOLD says there is a 59,071 registered large dams are there. And out of that, 65% of it is earth dam, 13% is rockfill dams, and the rest of it is gravity dam, ash dam, and other kind of dams. And these dams are constructed with many purposes. So I have just listed out world's highest earth and rockfill dams only, which is more than 200-meter dam. So the large dams are more than this, but if you see the Rogan Dam, it is 335, which is located in Tajikistan, and Nurek Dam, 300 meters high, and the Teri Dam, which is of 260.5 meter high in India, which is the highest earth and rockfill dam in India, and the third highest in the Asia, we can say. And if you see the construction of large dams in India, there are 5,745 total registered large dams available in India, out of which 5,334 dams have been completed, and under the construction is 411 dams. Out of this also, if you see here in the pie chart, you can say the Maharashtra is having the largest kitty, which is of 59%. And Maharashtra, if you recollect, the most of the land is of expensive soil. So even in the under construction kitty, the Maharashtra is having the highest dam constructed in there. Next is Gujarat, and we can say count on it. And if you see the history of a large dam in India, it started from, we are having oldest dam also, 1,000 years oldest dam also in India, like which is located in near to Trichy, where from this IGC 2021 is being managed, Kallanai Dam. which is even today it is being maintained very finely, and it has been improved ever since it has constructed by Sir Arthur Cotton also. We can discuss about it very in large, why it was required and how it has been maintained. And if you see, starting from 1900 onwards, this is the year 1971 to 1990, many large dams have been constructed. But this is the year where worldwide also and India also maximum, many of the dams failed also. There are lessons learned from the failures also. That also is an interesting topic to hear from. So if you see about the challenges and surprises in the hydroelectric projects, the challenges ahead are peninsular hydro and water resources development is reasonably good. Himalayan region has a bulk potential to be tapped. But as on today, the potential in Himalayas have been over-tapped, I can say, and the whatever sites available are with a lot of geological surprises and problems. And Himalayas, being the geologically young formations with the frequent changes in the rock conditions, are known for throwing up surprises. Geological surprises are one of the main cause of time and cost overrun and affects resource development. And over a period of time, with the experience, what I can say is we are hurrying ourselves to construct a project, and we are not doing proper geotechnical investigation, or we are not providing any time for carrying out geotechnical investigations, and we are taking as granted the sites available with us. That is why geological, when we are starting the excavations or when we are starting the project itself, we encountered with the geological problems. What are the geological problems? The variations in the lithology and the rock mass classification, variations in the projections because of the tectonic stresses, the problems in the rock formations, heavy and sudden gush of water like what we encountered in the Nathpa Jakdi and Dulhasti hydroelectric projects. Even today we are watching this, it is Nathpa Jakdi project has been commissioned, but even today we are watching, monitoring the behavior of the structure because of these problems. And geothermic problems, presence of poisonous gases like we encountered in the Ranganadi hydroelectric project, and shear zones, encountering shear zones in the foundation of the hydroelectric projects or the irrigation projects are very common. Like the famous one is Sardar Sarovar Dam, you must have heard about, and we had in Nathpa Jakdi also, and massive rockfalls in Nathpa Jakdi. It was very huge slide. This is the picture from the Nathpa Jakdi rockfall in the left abutment, and this is the slided rockfall which created problem for the construction of the dam. Because of that, the time taken for tackling this and then construction is high, and the cost overrun also is going to be very high. So what is the remedial measures to minimize the geological surprises? Actually, geological surprises occur due to a number of factors, and it is difficult to eliminate these factors totally. However, these can be minimized by adopting suitable means of planning, investigation, and design. For minimizing the geological surprises, we have to consider good construction methodology. We have to utilize good construction equipments. Construction sequences should be proper. Construction supervision is required, and proper quality control is required. With the experience, what we see is the quality control maintained at the projects has to be 100%. So, but we are lacking in that, and hurriedly we are constructing to finish the projects as quickly as possible. But that creates a lot of problem. Not may create, it always creates problem. Instead of finding a solution to a failed structure, it is better to construct a structure with proper quality control, and not we should not ignore the signals or warnings we are getting, unless and otherwise you are supervising during the construction of it or during the initial pre-feasibility stages itself. If you are not watching what is happening to the structure because of the construction of the structure, then you have to react to the signals we are getting. You should not ignore it. Contract formulations, it should be proper. Contract management also, we should not leave everything to the contractor and to wait for the fate of the structure to behave. And the instrumentation also, if the earlier days geotechnical instrumentations was not planned at all, but here with the latest technological developments, we can plan the geotechnical instrumentation at the early stage itself. Even if we are having a lot of structures which are 100 years of old or more than 50 years of old, which are requiring the renovations for each part of it. And we are having a dam improvement program, DRIP, with program through which every dams are getting renovated. So while renovation also, we have to plan for geotechnical instrumentation. And last week I have been to Punjab for visiting the Sirand and Rajasthan canal, which is two parallel canals running throughout the Punjab and getting water to the Rajasthan in Indra's IGNP canal. And that is 1960 it was constructed, and it is getting with the brick lining, and it is all the linings, most of the linings are damaged, so it is getting renovated. And in that also we have recommended for installing the geotechnical instrumentation for watching the seepage along the canal lining. And we have to do back analysis, and we should do documentation. And what I found is the documentation of each of the structure is very poor still now. So we don't want to show any documentation, so we have to document everything very properly. And in the dam foundation also, getting the geological surprises, it's not new. With the best sites for dam construction getting exhausted, geological surprises, complications are not uncommon in certain dam sites. The reason could be detection of buried channel, bands of karstic, marble, limestone in foundation abutments, like Bansagar project we got, and we get lower Subansiri project. In all stages we have got surprises there, and faults, geoshones, seams, bands with the shelly interactions, like in Kabi, Langbi, and Thobal projects we got it. And we have got in all the projects along the river Cyclic we are getting, and in Sunni projects and Luri projects also we have got shear seams. And weak abutments requiring intense strengthening measures for slope stability also, like in Latpa Jakri, the rock falls. And we are not, the fact is we are not investigating these abutments properly. So the proper geotechnical investigation is required, like the failure of Deton Dam, if you recollect, in 1970s or 80s. It failed. What is the reason for it, if you recollect it? So we learn lessons from all the failures also. So the geotechnical investigations have to be very proper. So the treatments required are found sometimes expensive. Some example with heavy cable anchors for Northpa Jakadi left abutment treatment we had to do. Extensive foundation treatment carried out in Gambhir Dam, Bakra Dam, Tista stage 5 dam, and diaphragms for ensuring seepage control in Soli Dam, and the liquefaction potential of the Pagaladia Dam. If you see, there is across the river Kosi a dam for multi-purpose, I can say, the Dagmara Dam projects, where it was a sand bed of great height, and the foundation was not very strong. So we have to provide a lot of foundation improvement, and the cost of the project was escalated like hell. So we have to terminate the construction of the project, though the requirement of the construction of the dam in that area was great need. So now again we are considering changing the dam axis. So we are doing that. So the geotechnical investigations for hydroelectric project, what we had to do, the foundation investigations is required for earth and rockfill dam, masonry or concrete dam, barrages, weirs, head regulators, canal and canal structures, powerhouse, tunnel, transformer caverns. And what is required is the subsurface investigation. We should know the location and details of the pits and the extent and the depth of the distance between the how many boreholes we have to drill across the dam axis, and how many axes we have to do only on the dam axis or upstream and downstream we should do, whether we can collect the samples from near to the dam axis for the borrow area investigations. Though it is going to be a reservoir only, there are specified rules and the procedures mentioned in the code IS 69555 we have to follow, and drifts completed along with the details of the field tests and geophysical test also. So when to do geophysical and when to do the extensive other field test, that is very, very important. And details of the rock samples, what kind of a rock is available, and from by looking at the with the help of the geologist itself and the type of rock and what is the extent of problem it is going to create for the projects, that is known. And the drill core collected together with the field rock mechanics and other in situ tests. In rock mechanics, we do the in situ test as well as the laboratory test also, and we should know selecting with the how the procedure is going to be. We have to be very careful about it. And the results should contain details of the observations in the field as well as the result of the laboratory and field test data, and the interpretation of the data, and suggestion of the treatments if any, if we foresee any kind of problems. And the soil and rock type, brief description of the overburden we should mention, information on the water table, rock type at the site, rock weathering, lateralization with its type, intensity and extent and effect of the excavation. Rock falls and landslides, we should demarcate the zones of the rock falls and landslides, magnitude of the landslide, and the estimate of the volume of the material involved in the slides. Such structurally weak zones also we have to mention it, and the stresses in the rock and the neotectonic features also we have to mention it. And the sources of construction of the materials like soil, sand, gravel, aggregate rock, lime, pozzolana, etc. shall be identified, and their mode of occurrences shall be indicated in the detailed project report. Details and the location of the auger or drill hole pits and drifts excavated are very, very important, and what all the in situ tests are conducted, that also should be mentioned. And for every kind of structure, the requirement of this is very, very important. As far as the in situ testing on the rocks, we have to conduct the in situ stresses like overcoring, hydraulic fracturing, and the shear strength rock to rock and rock to concrete to rock interfaces, and concrete to rock interfaces in dry state as well as the saturated state we have to find out. And the deformability characteristics like we can use plate jacking test, plate loading test, and the dilutometer test. And as far as the laboratory investigations on rock is concerned, we have to conduct these many tests, and in saturated and dry state also. So we have to start with the investigations for the hydroelectric project with the geophysical methods, and then we have to proceed for the detailed investigations. There are many geophysical methods are available, and we should know what it is sensitive to, what all the typical typical applications it can be used for, and what is the disadvantage or advantage of each of this test. Accordingly, we have to do. And what is the requirement of the project also we should know. And we do have many field tests like plate load test, standard penetration test, dynamic cone penetration test, electric cone penetration test, pressure meter test, vein shear test, field density tests and all. And as far as the water resources projects are concerned, it is mandatory to have the in situ permeability test, and what kind of in situ permeability test we have to do, and what is the infrastructure facility required for each of the tests. That is very, very important. And for yeah, like I said before, we should know the advantage and disadvantage of each of the test, the limitations of each of the test, and the limitations of the parameters we get from each of the test. Then we have to apply for the design. And while collecting the disturbed samples and undisturbed sampling also, we should be very careful. Normally, we make the contractors or the agency which we engage make mistakes in providing a proper drilling equipment and proper sampling equipments only. So we have to be very careful in choosing that. And if you see the relative test accuracy and the relative cost per test, the standard penetration test falls in the here, whereas this is the most the parameters we are getting from the SPT test is the most liked by the designers, where the costliest test is pressure meter test. We do have in CSMRS all these facilities, and we seldom use the requirement by the client for this test is very low, but we have to use this test in where the thermal power projects we do use it, and in the higher hydropower projects we do it. The costlier the equipment, the accurate the results are going to be. That is what we have to note it. And the characterization of the soil, starting from the grain size analysis, consistency limit, specific gravity, compaction properties, and shear parameters, one-dimensional consolidation, permeability, soil dispersivity identification, chemical analysis, and all. So consistency limit, as far as the earthen rockfill dam or embankment is concerned, we have to do the shrinkage limit also. So we have to be very careful while selecting the materials for as a borrow area material. And as far as the compaction properties also concerned, we can do the light compaction, standard Proctor compaction, or the modified compaction. Which density we have to use, we have to be very careful in that. And while selecting the type of test for determining the shear parameters also, we have to be very careful. But what we are seeing at CSMRS, all the detailed project reports, most of the 90% of it has the shear parameters evaluated by the direct shear test, and we should know the limitations of the parameter we are getting from this direct shear test. And which one we have to do, consolidated drain one, consolidated undrained with the pour water pressure measurements, that we have to see. And as far as the dams are concerned, while doing the stability analysis, what kind of analysis we are going, that depends on that. So accordingly, we have to choose the proper appropriate triaxial test and then perform the test. And it is mandatory for any water resources project to go for soil dispersivity identification test. As far as today, there are no Bureau of Indian Standard codes available for testing this. So we are following the Sherard's method of testing only, but the code is under formulation. Very shortly it is going to come, and but it is a qualitative test only. Yeah, this is the grain size distribution curve, which looks very simple, but it gives a lot of information. That is why we have to put in a lot of effort in doing this grain size analysis or mechanical analysis very properly. In most of the projects, what they do is they don't do the sedimentation analysis as per the code. They do the dry sieve analysis and they give a very wrong informations about the type of soil and the parameters like D10, D15, D30, D60, D85. These are all the sizes, grain sizes, which is very important as far as the water resources is concerned. The uniformity coefficient, the coefficient of curvature, and filter material suitability analysis, everything we can do out of this. And we can calculate the approximate coefficient of permeability from the D10 effective size, but we should conduct the permeability test and determine it. So going to the case study, Punatsanshu 1 hydroelectric project, which is located in Bhutan. This is where it is located, and it is a runoff river scheme and 70 kilometers away from Thimphu, the capital of the Bhutan. And the project contemplates the construction of a 136-meter high concrete gravity dam across Punatsanshu River. But the problem was the right bank slope suffered instability 3 times. If you see in July 2013, this portion has slided, and 2016 this portion slided, and the recent slide was 2019 slide, which it just slipped over this. And the entire area, the dam, if you can see, this is the dam axis. The spillway is being constructed just 100 meters away from here. It is to be abated in this left abutment, right abutment. So this is the portion where it slided. And what we see always is when it is slided, we always try to hide it and put more material on that and giving more stress to the slope. And this is the place where it slided from here. You can see the scarp. Yeah. You can see the truck which was toppled here, and whereas it was lucky that nobody got hurt. And this portion was to be analyzed because the dam spillway has to be averted on that and investigated. There was no way where we can do the testing on this failed area, and this was whole of this portion was vulnerable to slide. So we had to look for benches where in original places, and after each of the slide, these roads were, this is the highway which is catering to the public in Bhutan. So they didn't wanted to lose this highway, so they wanted to the Bhutan government wanted to reconstruct this one. So for doing the
Dr. Chitra, could you please, you have 2-3 minutes, you can kindly.
Okay, okay. So that is why we did this investigations going into the natural places. And then what we found was this is the entire, if we have to stabilize this entire slope, even the colonies which is constructed for here, one of the layer is going to be off. So we have to, based on the investigations, we have to shift the location of the dam axis itself towards the upstream side. There are also 2 occasions we have to shift. So as far as the Myanmar project is concerned, we can see straight away there are clay, gravel material, clays, and as well as the sand bed also, which was having a plate load test we did, which was having a very weak material. So because of that, we had to shift the dam axis. And sometimes we may have to abandon stop the construction of the dam itself. Idea of construction of the dam at that location also. We may not find any suitable site in the upstream as well as in the downstream also. Like that, many problems occurs. I'll straight away going to one more project, which is Bintudu Leshka project. The dam type was a concrete gravity dam, which was 67 meter high and 322 meter long, and which is having medium to coarse grained granite, ferrous granite niches, and it was having a shear seam, very interesting project. Shear seam of very wide one, up to 5 meter wide shear seam. After the excavation was in one of the blocks, it was there, and the dental treatment has to be planned on that, and then this project is under commission. And not only with the shear seam, the problem of the acidic nature of the water in the river also made a problem. So we are doing treatments for it is a hydroelectric project, treatment for this. And coming to the conclusion, proper geotechnical investigation for the best characterization of the strata and the construction material is required. Increasing reliance on parametric studies and judicious selection and input parameters. Expertise should be updated in design and as well as the construction. Pooling of experience by documenting problems encountered and the solutions adopted. No escape to sound judgment. Geological surprises are will be there, but we should plan and design up to mitigate those geological surprises. With this, I have come to the concluding. Thank you so much. And thank you very much for the organizing team of IGC 2021. It is my pleasure and my ministry's pleasure to be present, part of this IGC 2021. I have to thank, it is not my lonely work. It is entire CSMRS officers. I cannot put all this because it's all 150 people who had contributed to each of the projects. And thank you so much. Thank you. Sorry, I missed many interesting projects also. I am open for question answer if any is.
Sabina?
Yeah, it's very interesting presentation. It's actually she explained the experience and with her rich experience. She explained the need for the documentation of the lessons learned from failure. That's very important, and how to we have to disseminate this knowledge to the lower level, to the even to the budding engineers and students, so that once they face such problems, it will be useful for them. So I think the need of documentation is still very important. So it's very interesting, and thank you so much.
Thank you.
Yes, sir.
Yeah. Dr. Chitra is an excellent presentation. Of course, I also involved earlier some dam projects. One of the largest dam, Nurek Dam, I have involved actually. 2 months practice I have done actually. I know the difficulty of the construction of the dam, particularly larger dams actually.
Yeah.
I have only one question.
Yes.
In India, I involved a few nuclear projects for geotechnical characterization, like Kodangulam, Kalpakam.
Yeah.
There, usually we are doing investigation in 3 stages. In first stage, to finding suitability of the site for nuclear project. Then, after selecting the detailed geotechnical geophysical investigation, 3rd stage, that is after excavation at the founding depth, we are doing confirmatory geotechnical investigation. Is this the same practice or different in dam construction, particularly large dam construction?
Exactly, sir. For any projects, large or small projects also, there are constructed in 4 stages actually. Pre-feasibility stage and feasibility study and the detailed project reports, which the pre-feasibility study, any dams can be constructed on that site or not, with the available informations nearby and the geological formations. And we first of all fix up whether the dam axis can be fixed on that or not. That study is conducted. After that, whether materials are available or not, with the minimal investigations, geotechnical investigations and geological investigations, that is fixed. And then with the available, how much the design is done, and then how much material is required for each of the zones material. Then detailed investigation is conducted. And during the construction also, other than the quality control tests which are carried out, based on the material, we may be at the shallow depths only we find the characteristics. When you go deeper, those materials may not be suitable for the construction. So additional investigations is done during the construction stage. And then, of course, post-construction stage, of course, the behavior of the structure is studied. And yeah, we are doing investigations on that. This is what stage wise we do. CSMRS has done many projects for nuclear power projects also, like the power projects which is constructed in Haryana, we are involved with, and many. So there also again, the soil are, because very heavy machines are mounted on the soil strata or the foundation strata. So whether they are collapsible in nature, when the water table is going to be very shallow depth itself, then the problem goes many folds. So those kind of study also we had done. Yeah.
Thank you. There are few
I
questions.
think, yeah, few questions are there. One from Anil Cherian. Do you think that quality is sometimes influenced by political and other non-technical factors while executing a project?
No, actually it is about, I don't know, in my experience, what I would say is we are considering the quality control to be slowing the process or construction totally, but it is not like that. Meticulously, if you do the quality control also, it's not going to increase the time taken for completion of a project actually. Yeah, we are always hurriedly, I'll not say it is politically influenced. The persons who are, because I am from the government sector, so totally purely government officer. That is why in each of my slide, the 75th Amrit Mahotsav, I have to say, show it, and it is mandatory for me. So I will not say don't get influenced by anything. It is totally contractuals only, because the per day execution of work, the payment is made. So if you are strict and if you are available, if you are means if the quality control engineer is available at the site, he can control anything, and the time taken will be the same for as planned only. That is it.
There is another question also, ma'am. Can you shed some light on seismicity induced due to large dams?
Yeah, we have been hearing about this a lot, like Koina Dam and all. I think I cannot say positive or negative also to it. Sorry, I won't be able to give my comments on that. I would like to, as an expert, I would like to keep that comment with me. Thank you.
Sir, there is no more questions, I think.
Bina, conclude that.
Yeah, it was an excellent presentation. Thank you so much.
Thank you so much. Thank you so much.
This organizing committee, I thank Dr. Chitra for your presence here and sparing time with us.
Thank you so much.
Thank you so much. So shall we move on to the
Yeah. So next presentation by Professor Buddhima Indraratna. Professor Indraratna, kindly join the. Yeah, Professor Buddhima Indraratna is a well-known person. Of course, particularly is regularly giving keynote lecture all our conferences. And of course, several of our students are also doing PhD under his guidance. I briefly introduce his data. Professor Buddhima Indraratna is a founding director, ARC Industrial Transformation Training Center for Advancing Rail Infrastructure, as well as director for Transport Research Center of University of Technology, Sydney, UTS, Australia. He is a world authority on the application of fundamental and applied geotechnical research to the development of railway infrastructure. And he is passionate about training young engineers to become masters of railroad design and construction. He has published over 850 papers, including 12 books and about 450 journal papers, and has delivered over 80 invited keynote papers on all contents. His outstanding contribution to Australian transport geotechnics have been recognized by several prestigious awards, including the Business Higher Education Roundtable Award, hosted by the Australian Commonwealth, and Engineers Australia Transport Medal in 2011. In 2009, he delivered the prestigious E.H. Davis Memorial Lecture of Australian Geomechanics Society for distinguished contribution to theory and practice of geomechanics. And of course, internationally, his significant contribution are reflected by many awards. For instance, first Ralph Proctor Lecture in 2016, fourth Louis Menard Lecture in 2018 of the ISMG. Then the Thomas Telford Premium by the UK's Institution of Civil Engineers in 2015, Robert Quidley Award from the Canadian Geological Society in 2012, and the Medal of Excellence for Lifetime Contribution from the International Association of Computer Methods and Advances in Geomechanics. So I'm happy to chair this session where Professor Indraratna is presenting. Now I welcome Professor Indraratna to make presentation on the topic internal instability and fluidization of subsoil, subgrade soil under cyclic loading. Professor Indraratna.
Good morning, India, and it's afternoon in Australia. I hope all of you can hear me. Professor Bhuminathan, can you hear me?
Yes.
Okay, and is my slide clear?
Yeah, it's clear.
Okay, all right. So before I start, I would like to thank profoundly the ICG 2021 organizers, and also I sincerely apologize for postponing this lecture to today. It was meant to be yesterday, but as I've told the organizers, I had to attend a funeral of a family member yesterday in Sydney. So thank you very much for giving me this opportunity to present this now. I would like to acknowledge my co-authors, Dr. Mandeep Singh, Dr. Thang Truong Nguyen, Professor Cholacha Trujikiat Kamjon, Dr. Rakesh Sai Maliseti, and PhD students Joseph Arivilagan and Lakshmi Nair. The contents of my presentation will be divided into just 5 parts. The introduction, I will introduce what this fluidization concept is. I will go through some laboratory investigations, parts of numerical modeling with finite element and distinct element techniques. Then I will go through the industry impact that this research has already made, followed by some simple conclusions that are of relevance to those who are listening to me today. As you can see from this Australian map, which is on the upper left-hand corner of this slide, the eastern part of Australia, especially the eastern state of New South Wales, is where the population is most congested. And that is also where we have a lot of railways and roads, especially those that are built on soft soils and coastal estuarian silts and clays that are, which we normally call problematic due to very high settlements and causing differential settlements when it comes to long railway tracks. If you were to look at the the development of various transportation modes, you will see from these graphs here that the amber color plot takes off rapidly compared to the blue and the gray. And this amber color plot is actually the railways compared to roads in blue and then coastal shipping, which is gray. So while roads and shipping have been relatively stable, rail transport has taken off substantially since around 2010. And therefore, the last 10 years, a lot of effort has been spent by the government, the public sector, and researchers in improving the Australian railways. But one of the biggest problems that we face in Australia is this phenomenon of mud pumping. Now, if you were to ask me 20 years ago, we talked very little about mud pumping. But during the last 10 to 15 years, the axle loads of our trains have almost doubled, especially the heavy haul trains. The length of the trains are now sometimes over 4 kilometers long. So they can drag up to 70,000 tons in just one train with 350 to 400 carriages. And that kind of cyclic load will fluidize the soft subgrade, pump it upwards, and then pollute the ballast, as you can see from this particular picture. Of course, if you were to have a careful look underneath a concrete sleeper, you will find there are gaps opening up, and then the bearing capacity underneath the sleepers will be lost because of this. Now, in order to look at this mud pumping phenomenon in greater detail, you can look at the dynamic filtration apparatus and the dynamic loading facilities that we have at UTS Transport Research Center. Now, this is a unique equipment which has been designed and built in-house, and you can see that this particular equipment can apply a hydraulic gradient from the bottom to the top, which will make the water content change internally within the sample and then induce fluidization at the top of the sample. I will go to the details and explain this in greater detail later. But the important thing is that both the cyclic stress and the cyclic strain can be very accurately monitored because this dynamic actuator is connected to this automated computer control system. So here is a larger section of this equipment that you can see. You can see the pore pressure transducers at different points in the sample. So you can measure the hydraulic gradient from point to point. And as you can see from the schematic diagram on the right-hand side, P1, P2, P3, etc., they are the location of these miniature piezometers that enable us to look at the variation of the hydraulic gradient across the depth of the entire sample and thereby detect the locations of instability across the sample length. Now, if you were to look at this slide in a little bit more detail, what is plotted on the left-hand side graph on the vertical axis is the excess pore water pressure gradient against the number of cycles on the horizontal axis. You will see that the excess pore pressure gradient is higher for the top layer 2-1. You can see that, which is called layer 2-1, the hydraulic gradient is greater. As you go downwards, then the excess pore pressure gradient tend to decrease. Now, this actually tells the story, what I indicated earlier. That means when you apply a cyclic loading, there is a mismatch of the loading distribution with the depth of the sample. So then there is a disparity of the hydraulic gradient that becomes non-uniform across the depth of the sample. As a result, fine clay particles can now migrate from bottom to the top, and as a result, the water content will tend to increase towards the top. Why is that happening? Because the fine particles have a high specific area. Higher the specific area, greater the moisture these particles can carry. So when these fine particles migrate to the top, then the water content inevitably increases at the top layers. So you can see this again from this left-hand side diagram here, and you can see on the right-hand side diagram, you have the interface at the top, the middle of the sample here, and then the bottom of the sample. You will see that the water content will actually change when you go from top to the bottom, especially if you have a geotextile placed on the interface. So the idea is that if you have a geotextile placed on the interface, that higher water content that provides a greater pore pressure that you can see from these blue lines here, this greater pore pressure now will dissipate to these black dots here because of the geotextile. So the idea of the geotextile is to dissipate this extra pore pressure at the top of the sample so that the geotextile can try to prevent the fluidization of the top layer of the sample. In terms of practice, experimental evidence can also be obtained from the laboratory testing, as you can see from the laboratory triaxial sample. So what we do, we excavate close to a railway track in real life, bring undisturbed samples to the laboratory. We prepare these 50 millimeters by 100 millimeter triaxial samples, and then subject them to cyclic deviatoric stresses, as you can see from this particular plot here. And when a sample fluidizes, you will immediately see that the fluidization is a function of the top part of the sample. If you were to look at this sample carefully, you can see that the bottom part of the sample have actually consolidated. That means the water content will go from bottom to the top. The water content will decrease at the bottom, leading to consolidation. And the water that is expelled from the bottom layers will now be migrating to the top, increasing the water content at the top. And when this water content approaches the liquid limit, then the sample will fluidize. As you can see here in this insert of the sample, you can see the fluidized sample when you look from the membrane. So one of the other identifying factors in a sample fluidizing is that the sample will soften. In other words, the deviator stress in cyclic loading will actually take a plunge, as you can see in this diagram here. The drop in the deviator stress is significantly noticeable for different values of cyclic stress ratios. And this drop in the deviator stress is particularly significant if the cyclic stress ratio is greater, and that is what causes mud pumping to some extent, and not really the smaller values of CSR. So here is the larger picture that is indicating this mud pumping phenomenon. You can actually see very clearly the top of the sample is a slurry. It is a fluid, it's a slurry, and that is the sample that is taken from here. And again, the bottom of the sample has actually consolidated because the water content changes from the bottom to the top as the water migrates from the bottom to the top. So more information of this can be found in the Canadian Geotechnical Journal. This particular paper was the Editor's Choice Best Paper, as also one of the Robert Quigley Commendation Awards this year. And this is for the first time, in my view, that the mud pumping phenomenon was explained in a very simple way with internal migration of the water from the bottom to the top, and how the water content become close to the liquid limit. So very simple phenomenon. And we have not only verified this in the laboratory, but we have verified this in the field as well, where we found that it's the shallow layers of the subgrade soil that actually become fluid and not the deeper soil strata. So putting all these things into perspective in some nice plots, the liquidity index is plotted on the left-hand side vertical axis against the top, middle, and the bottom locations of the sample. So as you can see from this particular plot, when you go from the bottom to the top of the sample, where a sample becomes unstable, the liquidity index increases rapidly. And the liquidity index becomes closer to 1 when the water content reaches the liquid limit. So when the water content approaches the liquid limit, of course, the liquidity index becomes close to 1, and that's when we get mud pumping, as you can see from this picture here. Whereas in a stable sample that undergoes undrained yielding, but not mud pumping, then that distribution from the bottom to the top is not that significant. If you can see a very stable sample, which is the initial state, in the initial state, everything is flat, because the liquid water content is equally distributed from the bottom to the top. But a stable sample, you will still have some water content changes inside the sample, but not to the extent of what you see in this unstable sample that initiate the phenomenon of mud pumping. If you were to look at this in a particle size distribution point of view, when you take samples after failure from the top, bottom, and the middle, and you plot the particle size distribution curves on this right-hand side picture, you will see that the finer particles are greater at the top, as you can see from this red arrow here, whereas at the bottom, it has less of the finer particles. In other words, the finer particles have migrated from this bottom to the top, and thereby increasing the finer fraction at the top, causing this mud pumping phenomenon. So here is another way of looking at it. What is plotted on the vertical axis is the difference of the liquidity index between the top and the bottom, normalized to the liquidity index at the bottom. So of course, when this difference is significantly high, you can see that mud pumping is almost expected. You can see this red line, how rapidly this difference between the top and the bottom liquidity index rises, and that causes mud pumping here. Now, a stable sample will not have much of a difference between the bottom and the top, as you can see from this picture, from this bottom plot here. Now, I have put this in a summary graph, and you can find more of an explanation in my publications. The excess pore water pressure and the axial strain are two indicators that can give you the telltale signs of mud pumping. Now, at this stage, I want to make a very important comment, and that is undrained yielding is not the same as fluidizing. Most soft soil samples, when you put it to a triaxial cyclic loading test, they will yield in plastic, with plastic strains. They will undergo yielding, but they will not mud pump. Most of the samples will undergo undrained yielding with large plastic strains, but that doesn't mean that they become a fluid. In order to make sure that you see the difference between fluidization and undrained yielding, you have to look at both the excess pore water pressure change as well as the axial strains. Both excess pore water pressure rise and the axial strain rise have to become unstable for you to meet the criterion of the possible mud pumping. So in this case, there are several types of soils being considered here. Plasticity index of the soil varies from 10 to about 80. Where the clay content is very high, you have very high plasticity index, say between 40 and 80, and those samples are very stable. So higher the clay content, greater the cohesion and greater the resistance for the fine particles to segregate and move upwards from bottom to the top. But when the plasticity index is less, where the clay content is not sufficient to hold the particles together, then the fine clay particles and the fine silt particles can then travel to the top, increasing the water content and therefore increasing the excess pore water pressure and rapidly increasing the axial strains to failure. And if you open the membrane and check, you will find that these samples have actually fluidized. Now, the effect of loading and the cyclic stress ratio is very important. The cyclic stress ratio is the ratio between the deviator cyclic stress divided by 2 times the confining pressure. So if you were to plot the cyclic axial strain for different values of cyclic stress ratios, in this case between 0.3 and 0.5, and you vary the frequency from 1 Hertz to 5 Hertz in this case, you can see a series of graphs where the cyclic axial strain becomes relatively stable, as you can see from these bottom curves, even up to 10,000 cycles. Then these samples become stable and they will not be subject to mud pumping, but they will certainly be subject to undrained yielding. So the undrained yielding will always occur because there are plastic strains taking place. So that you cannot prevent. But not all the samples will be subject to mud pumping. But these 3 samples that you see here were subject to mud pumping and they will fail by the sample fluidizing. And you could see that very clearly from the excess pore water pressure diagram here with time, where the excess pore water pressure keeps on increasing. Whereas in the stable case, where you have 5 Hertz frequency, the excess pore water pressure becomes relatively stable, as you can see from the green lines. So again, my point is that you need to look at both the excess pore water pressure rise as well as the axial strain rise in order to distinguish mud pumping from undrained yielding. So here is the effect of soil compaction. One way of physically preventing the question of mud pumping is, of course, by compacting the soil to a significant dry density. In this particular case, when the soil has a dry density of almost 1800 kilograms a cubic meter with a relative compaction of 99%, then you will find that the maximum incremental pore pressure change is actually relatively constant. In other words, the rate of gain on pore pressure is marginal. Whereas if the dry density is relatively low, or the relative compaction is, say, around 85%, then the chances are that these specimens will mud pump with about 5% axial strain, as you can see from the top graph here, where the incremental rate of pore pressure rise is substantially high in this graph compared to this plot here. Putting all these things into one particular graph, I was it is coincidental that Professor Bhuminathan is actually the chair of these sessions, and I'm quite pleased to plot your results here as well, Professor Bhuminathan. You can see some of your 1988 results. I have taken data from many countries here, and they have been plotted. They are coming from India, China, Canada, Australia, Vietnam, and so on. And they have all been plotted in this particular chart with the plasticity index plotted on the vertical axis with the liquid limit on the horizontal axis. You will find that irrespective of the country, that the soils that are vulnerable to fluidization are those which have a liquid limit less than about 50% and a plasticity index less than about 30%. Beyond that, there are very few soils that will actually show fluidization. But of course, the soils that plot here will be subject to undrained yielding, just like any other plastic soil. But if you were to take the soils in Australia, I will put a line about liquidity limit less than about 35% and the plasticity index less than about 20%. So the Australian soils that mud pump are falling within that band there. So how do we prevent mud pumping in a practical situation? Well, first thing that comes to my mind is the use of vertical drains. If you were to put vertical drains into these soft soils, then the vertical drains will rapidly dissipate the pore water pressure, irrespective of the cyclic stress ratio. Here is applied from 0.2 to 0.5 with and without PVD. When you do have the PVDs, you will find that the maximum pore water ratio stabilizes very quickly, and the pore pressure actually decreases to a zero even after 10,000 cycles. Between 10,000 and 100,000 cycles, you can see that the pore pressures have duly dissipated as expected. But if you do not have the vertical drains, then when the cyclic stress ratio exceeds 0.3, you are bound to get failure by fluidizing, as you can see from these two curves here. But of course, even without a PVD, if the cyclic stress ratio is only about 0.2, that cyclic stress ratio is not high enough to cause fluidization. So the pore pressures will actually stabilize. Even though you don't have a vertical drain, the cyclic stress ratio is not high enough. So what is the story here? Well, the story is if the cyclic stress ratio is only about 0.2, it is not a heavy haul train. That's a train with a very light passenger train or very light axle load train. So it is not going to cause mud pumping because the CSR value has to exceed a threshold value in order to cause mud pumping. So here are some large-scale triaxial testing with vertical drains put into these large samples, which are 0.5 meter diameter and 1 meter high. You can see this large-scale dynamic triaxial equipment with the vertical drain in the middle. And again, it's the same thing that when you don't have vertical drains, the pore pressures will rapidly go up, and then you will get fluidization in these samples without PVDs. But when you do have the prefabricated vertical drains installed, then the pore pressures will rapidly dissipate, and then you get stable excess pore pressures with time. And of course, if you look at the volumetric strain, where there are no drains, then volumetric strains are zero because these are perfectly saturated samples. So you cannot have volumetric strains. So the volumetric strains are practically zero. But when you do have vertical drains, then you get consolidation of the samples, as you can see from this plot here. So with this consolidation, you increase the shear strength of the sample, and also you prevent the fluidization phenomenon. Putting all this into a real life application, this is the town of Sandgate, very close to the city of Newcastle and north of Sydney. Short vertical drains were put into this estuarian plain so that a railway track could be constructed on this estuarian plain. You could see the finite element model. In this particular case, the software was Plaxis, and you can see the soft soil 1 and the soft soil 2 layers. The shallow soft soil is the lightest or the softest, and the soft soil 2 below is slightly more dense and slightly more over consolidated than this normally consolidated upper Holocene clay layer. So you could see from the pore pressure diagrams here that when you don't have prefabricated vertical drains, the pore pressures tend to be higher with time. These are the measurements. And when you have the PVDs or the vertical drains, then the excess pore water pressure values tend to be less compared to the case without the vertical drains. You can find more details of this paper in ASC Journal of Geotechnical and Geoenvironmental Engineering 2010. So here is the same Sandgate railway track case. This is the finite element analysis. You can see the very soft alluvial clay at the top, and the blue vertical lines are the short vertical drains. And this railway track often gets flooded. As you can see from a flooded day here, you can barely see the railway track. Everything else is water, completely waterlogged. And then once the flood water recedes, you would expect the trains to operate. And then in this particular case, the Australian Railway Track Corporation wanted me to actually make a prediction of how this track is going to behave. So I did these predictions with Erupt Geotechnics at the time. And then my predictions for settlements are what you see from this dash line here. 1.5 years later, when the track was constructed, then the settlement points were given to us. So the plotted field data you can see from the circles here. For all practical purposes, that was a pretty good prediction. Now, in terms of excess pore water pressure, so it is the same story as the previous graphs here. You can see the excess pore pressure would be less when you have vertical drains, and these are plotted here as an average. If there are no PVDs, then the excess pore pressures are high, and when you have the PVDs, then the pore pressures dissipate rapidly. In addition to that, having the PVDs will reduce the lateral displacements. If you did not have PVDs, then the lateral displacements will be very high, causing mud pumping. But when you have the PVDs at 1.5 meters spacing, then this red line gives you the lateral displacements, and the dotted lines are the subsequent measurements 1.5 years later. And again, for all practical purposes, that's a very good prediction. Now I'm coming to the last stage of my presentation, the use of DEM modeling. Now what I'm going to show you is how in a railway track, when you have a subgrade soil with an overlying granular particles such as ballast and subballast, how do you increase the hydraulic gradient from bottom to top in order to create mud pumping simulation? So let me run this first, and at a delta P of 200 kPa, so that's a pore pressure differential, you will see that the subgrade soil will fluidize, but the hydraulic pressure is not enough to come to the top. Whereas if you were to increase the pressure gradient, then the soil will mud pump and the fluidized soil will come to the top of the ballast, creating this mud pumping that you can see on the top of the railway ballast. So you will ask the question, what case is more dangerous? Well, I would say that case is more dangerous, the one on the left-hand side, because the railway drivers, the train drivers cannot see the mud on the top. Whereas at least in this case, the drivers can see the railway to a distance, they can see the mud pumping has occurred and can warn the subsequent trains to be careful or not to operate at all. So putting all of these things together, the next step is to develop a micromechanical computational model. So there are three things that go into this model development. The stress conditions, the cyclic stress conditions have to be merged with the hydraulic characteristics of the soil, and then the geometry of the track all have to be combined to come up with a distinct element model that you can see from the right-hand side. And as you could see from the previous model, that when you have upward hydraulic gradient, your top of the sample can get fluidized, and then you get heave, as you can see from this schematic diagram here. The more details of this paper you can find in Nguyen and Indraratna 2020, a coupled computational fluid dynamics and distinct element method approach. So here is a, thank you, thank you. I'm going to increase the discharge velocity, and I'm going to increase the internal fluid pressure gradient at the same time. So you can see the discharge velocity and the fluid pressure gradient increasing while the sample is fluidizing. You can see the discharge velocity is increasing, the fluid pressure gradient is changing, and the sample is now fluidizing, and the subgrade soil, there's so much heave here, and the railway track has actually failed in this particular case. So coming to the conclusions and practical implications, in Australia, in the state of New South Wales, soils which are low to medium plasticity or the PI values less than 30 are the ones which are most vulnerable to fluidization. But when you have an increased clay content, that favors undrained shear failure, but without fluidizing. But again, I emphasize, all plastic soils will undergo undrained yielding, but only very small number of them will actually be subject to fluidization, because the water content has to become equal to the liquid limit, or the liquidity index have to become 1 before you can get the fluidization condition. So the fluidization mechanism is the internal migration of water content from bottom to the top, whereas the water content at the top layers will become larger and approach the liquid limit, and the liquidity index becomes 1, then the sample becomes a slurry. The cyclic stress ratio has to initiate fluidization when the CSR value exceeds the critical value. In these samples that I showed you, that value had to be greater than 0.3, closer to 0.4. So for heavy haul trains in Australia, a cyclic stress ratio of greater than 0.4 is quite dangerous unless you have stabilized the soft soil. The frequency is secondary. Frequency can be corroborated with the train velocity. So if you have a very heavy train, even if it goes at only 60 kilometers per hour, you can still get mud pumping. It doesn't have to go fast. So the important thing is that the cyclic stress ratio is the primary factor, whereas the loading frequency is secondary. Fast, lightweight trains with low CSR but high frequency will not have enough time for critical pore pressures to develop in the soft subgrade. Therefore, they will not be mud pumping. In order to prevent mud pumping, short PVDs and geotextiles can be put to dissipate these pore pressures effectively. I would finish my presentation by acknowledging the Australian Research Council for supporting this research for more than 2 decades. The industry partners, quite a large number of them, both railway track owners and private geotechnical companies and public organizations that have assisted us in this research. The hard work has always been done by fantastic PhD students and research associates. Many of them, I'm proud to say, actually come from India. And UTS Transport Research Center, where I work now, is, I'm proud to say, is one of the largest transport research centers in the world today, with iconic facilities for this testing. Thank you very much. I have 7 seconds still left.
Thank you. Thank you, Professor Indraratna, for your excellent and interesting lecture. Of course, I have listened in several conferences in India as well as in abroad. All your lectures are very useful, particularly both the numerical laboratory as well as field application, where we are not doing. Some of them we are concentrating filters, some of them in laboratory. But like you, who are focusing all aspects is very nice, very useful for us actually. I have only one question before going to others. Did you try for any other growth improvement methods to prevent fluidization other than PVD?
Yes, I think, as I said, PVD was one, and PVD, short PVDs are absolutely necessary where the water content is almost close to the liquid limit to start with. For example, if you are going to improve a floodplain, what we call crocodile land in Australia, if you like, the water content is naturally close to the liquid limit. So in situations like that, you can't just put a geotextile and expect the pore pressures to dissipate. That's not going to happen. So in such cases where the water content is naturally close to the liquid limit, you will need PVDs. Other situation where the water content is notably lower than the liquid limit, you might be able to manage with compaction, as I showed earlier, with a higher dry density, or by simply having a drainage geotextiles. So there are three methods which we have tried out. Now, you might think that by stiffening the ground with lime piles, deep lime mixing, and so on, you can prevent mud pumping. It is possible, but we haven't tested them in the laboratory. But these are the three methods that we have tried, and they have worked under different circumstances. So it's compaction, use of geotextiles, especially for the shallow subgrade layer, and then PVDs, where the water content is almost close to the liquid limit to start with.
Thank you, Professor Indraratna, for explanation. Of course, I thought we would have done some solidification also. Professor Beena, do you have any observation?
Thank you very much, Professor, for the excellent presentation as usual. I am very happy and felt fortunate to share this platform with you and see you here. I felt a little bit nostalgic also yeah, when I see the labs. Okay, so I have a small clarification I need. Whether the high-speed trains are more liable for this mud pumping or than the ordinary trains?
No, actually, that's quite the opposite. That, as I said, the cyclic stress ratio has to become critical for mud pumping to occur. In all our tests, Professor Beena, that the speed of the train not necessarily creates sufficient pore pressures. For example, you saw my frequency chart that if you load the sample at 5 Hertz frequency, the pore pressures are actually lower than 1 Hertz. Because if you can assume that a train can go extremely fast, by the time the pore pressures develop, the train has already gone. So whereas an extremely heavy train will give enough time for the pore pressures to develop because the axle loads are much higher. So the heavy haul trains going at a slower speed, of course, will create a greater mud pumping risk, if you like, than a lightweight passenger train. Of course, at the same time, if a very heavy haul train, if you try to increase the speed, I think the train might fail because of other things and not because of mud pumping. So my argument for my answer to that is that if you have a joint network where the passenger trains and the heavy haul trains are sharing the same network, you got to be pretty careful, because a heavy haul train can first go and damage the track, and the mud pumping may have occurred, and the driver may not have even seen the mud because it hasn't come to the top. But then 15 minutes later, you get a crowded passenger trains. And that might be a danger because that passenger trains will be going on a sponge, which is already failed.
Hi, Buddhima. I just wanted to say hello.
Hello, Professor Madhav. Nice to see you.
Great lecture, as usual. Good.
Professor Madhav, any observations?
No, I think we can't say anything about what Buddhima. It's the last word.
Professor Nathan.
Yeah.
We have to finish the session by 11:10.
Okay.
And as per the information received from the organizing chapter. And we have one more presentation, corporate presentation.
Okay.
From other two presentations which has been listed here. One of them is already done yesterday, and there is no confirmation from complete instrumentation solution. So you may invite Heiko for the presentation.
Just before going to the corporate, just on behalf of the organizing committee, I'd like to thank Professor Buddhima for even the difficult time he has readily shifted his schedule, and even I don't know. It is a great loss in the family. So on behalf of IGC 2021, we deeply express our condolence to you, sir. And
Thank you so much.
thank you so much for accepting, really accepted and shifted your schedule to today. I'm really, I mean, that shows your commitment towards IGS and IGC. Thank you so much on behalf of the organized committee.
Thank you, Dr. Muthukumaran. Thank you very much for giving this opportunity. And please tell your audience, anyone who has a question, please send me an email, and I promise that I will respond. Thank you so much, and very nice seeing you all.
Thank you, Professor Indraratna, for your wonderful presentation. And thank you, Dr. Chitra, also for your nice presentation. Now we are moving to the corporate presentation. I invite to Heiko. Yes, Mr. Professor Solanki. I invite to Heiko.
Yes, you may invite Heiko.
Yeah.
And time for the presentation is 5 minutes.
Yeah, 5 minutes. Okay.
Okay. Good morning, Professor Chandra Solanki ji. Good morning, ji, and good morning to everyone who is attending this session today. I was hearing the previous session, and it was very nicely done by the professor. And I'll just share my screen here. Okay. Is the screen visible?
It is not in sliding mode.
You make it full screen. Okay, it is good now.
1 second, sir. This is okay
it is
now?
Good now. Yes, good.
Okay. First of all, Heiko welcomes all delegates of IGC 2021 Trichy chapter. And I would like to thank Dr. Muthukumaran, who gave us the opportunity to become the platinum sponsor for this event. Heiko has been associated with the IGS since its inception. This was before before me. My grandfather, late Sardar Resham Singh, used to take care of this. Then my father, late Sardar Mr. Jatinder Singh, who left us last year. And now the complete operations and is being handled by me and the team of Heiko. And as we are known in the market for innovations, so the legacy of the innovation is going on. And today also, I mean, like I will be showing you two few slides where we have added new products, mainly for the geotechnical engineering. So this is like, I was just going through my papers and I saw this where this is a direct shear machine where in the University of Ghent. And this is basically innovation since we are basically focused on innovating things. So this is what a direct shear used to look like when it had started. So this picture I had somewhere in my data. So I thought I'll just put this idea here so that how innovation started and how it is right now. So if you see this slide, you can see there is a cycle wheel, which is used as a normal loading mechanism for putting the weights and all. And then you have this assembly where you have this LVDT dial gauges attached along for measuring the displacement. So this is the conventional shear box which is being used nowadays. This is a totally manual. This is a manual shear box where the horizontal and the shearing loading is totally controlled through a gearbox system. It's a 12-speed gearbox system, which is having a 60 by 60 mm shear box assembly, and it is having a you can even add a load cell here for measuring the load, and if not, you can have a proving of a capacity 200 kg. This is a totally this is totally this is a new kind of a shear box that we have come out maybe like it was like 2 years back. We came out with this, where the normal and the shearing load is totally programmable. You can control both the loads, normal and the shearing load. where the minimum strain rate is 0.001 mm per minute to 10 mm per minute. And this shear box is completely designed as per IS 2720 and BS 1377. We are using servo motors in this. Earlier we had been using stepper motors, but for a better speed range, we have now shifted to servo motors. The horizontal and the vertical displacement are being measured through LVDTs, and you can see in the photograph. The right side, you can see the software screens where you can measure the specimen ID, length, width, thickness. Everything is on the system itself. You just need to put in the data and you can have an analysis software along with the system. So this is just a closer view of the LVDT and the displacement transducer setup that I have for this system. This is an automatic shear box, again a size of 300 by 300 mm. This we did for IIT Delhi, where the normal and the shearing load is totally programmable. It is used for studying the CNL and CNS conditions both, where CNL is being used to for planar rock joint only, and CNS is used for non-planar rock joint and reinforced slopes. So these are the conditions for both CNS and CNL. So this is the shear box assembly, where the normal and the shearing load is applied to we use servo hydraulic actuators here. It is working on a closed loop feedback principle. The upper box can move only in the vertical direction, and the lower box is having bearings which can move in the horizontal direction. These are the components of the shear box. Then this is again a newly developed shear box that we have done, where again the normal and the shearing load is programmable. It can accommodate a sample size of 300 by 300. It's over. Again, this is some of the software screens. This is the large shear box that we did for mines. Again, a size of 750 by 750 by 1 meter, where the normal and shearing load is again programmable through the software. And it is the same shear box can accommodate a size of 300 by 300 also. So these are some of the features of the shear box. This is a rock triaxial system of capacity 200 tons, where the confining pressure is being applied through a hydraulic pressure system, which has a confining pressure up to 7 kg cm square. And this cell can accommodate all sizes of rocks, AX, NX, EX. And again, this is totally programmable. This is the confining pressure unit.
Mr. Ranuk Singh.
I'll just take 2 minutes, sir. I'll just take 2 minutes.
Okay, okay.
So now this is a new this is a new deformation setup that we have come out with. This is basically under triaxial test of rock. Now, earlier people were using strain gauges for measuring the deformation in triaxial testing. Now we have come out with a new attachment where you have these LVDTs. These are high pressure LVDTs which can go up to a 70 MPa, that is 700 kg cm square, and we have seen the results. They are fantastic. This is the hydraulic cyclic setup that we have. These are the software screens. If you see, this is stress versus time, where and this is the pneumatic system that we have. Now we have developed an electromechanical system also, and it is running well at ISM. And even the normal and in this case, we have 2 controllers, both of 2000 kPa, and these are touch panel controllers. These are the specifications of the load frame that we have. These are the controlling units for confining and back pressure. A volume change device is also given along with it. Some of the accessories that we supply. These are the software screens of the cyclic system. Now, this is a new development that we have done is Cyclic Simple Shear, where the normal and the shearing load is totally programmable, and you can apply both load static as well as cyclic. And this is totally as per ASTM 6528, where you have all the critical features like active height control, lateral confining pressure system, pneumatic actuators, and it is used for studying the dynamic properties of the soil, including shear modulus, damping simulation of different types of field conditions and non-cohesive soils. So with this, I would like to end my presentation. And if anyone has any queries or any discussion is to be made, we are available at the stall. You can visit and we can have a further discussion there. Thank you so much for your valuable time, and we look forward to see you in actual, not on virtual setup. Thank you. Thank you, sir.
Thank you, Mr. Ranak Singh, for presentation.
Yeah.
Hope that our delegates will visit your stall. I think we are crossing the time actually. So Sabina, I think, has some problem. So we had 3 interesting keynote lectures delivered by very internationally reputed academicians and also director of CSMRS. And I thank all the keynote speakers for presenting lecture and spending valuable time to be part of the IGC 2021. I thank the organizers. I thank the participants to listening all the lectures, with also asking several questions to the speakers. Finally, I thank myself and Professor Bina, Professor Kumar and other organizers of IGC 2001 for giving opportunity, and also thank Professor Solanki coordinating the session. Thank you.
On behalf of the organizer. Okay, madam. Yes, please.
Yeah, thank you so much for the opportunity the organizers has given to me for co-chairing this session. Once again, wish you all a very happy new year.
Thank you. Thank you.
So, on behalf of the organizer,
I'll see in the next IGC 2022 at Kochi. I take this opportunity to welcome you all to Kochi also. So thank you very much.
on behalf of the organizer, I session coordinator, Professor Solanki. Thank you, Professor Nathan and Professor Bina. I request all the participants and delegates to proceed for the next session. Thank you. Thank you all.
Thank you.
Thank you so much,
Thank you.
Professor Solanki, for conducting this session very nicely. Thank you, Chair and Co-Chair. Thank you all the keynote speakers. Thank you all the participants. Please join with us for the respective. Thank you once again.